Let's have a look now at DAC problem number 6, which was the one that's starting to get a little bit more realistic in terms of the number of bits we are using, and maybe not quite as realistic as far as what their values are, but what we have is a 7-bit binary weighted DAC, D-to-A converter, with the bit values here, and here I mean the weights, and these might be set by the resistors or current sources or whatever. But they're 1 LSB, then twice as much, then 4 times as much, then 8 times as much, and it should be 16. The 1, 2, 3, 4, 5th bit should be 16, but instead it's 15. So the weight of that particular level or individual bit, whatever the components are that make up that that part of the D-to-A converter, should be 16, but it's 15 instead. Then the next one should be 32, but instead it's 33. And the last one should be 64, but instead of 62. So this one, the 1, 2, 3, 4, 5th bit is a little too small. The 6th bit is a little too big, and the 7th bit is, got a little bit smaller than it should be. Now, if you look at the percentage of, how much each one is off, right? So for the very small ones, focus here. All right, for the low level bits, the least significant bits, they're all fine. We get to 15, and it should be 16. It's only 15, but that's off by 1/16, which is 6.25%. So that's not, to be honest, it's off by a whole LSB, but it's not significantly terrible as far as if you were picking resistors and we're trying to get a 16K ohm resistor and you measured it at 15. You might end up, if that's a 10% resistor batch, you could end up with that. 33, it's only 1 out of 32, so that's about a 3% error on it, and 62 should have been 64 is 2. That again is a 2/64, so 1/32. That's again about a 3% error on those. So, these are not beyond the realm of possibility if you're building a, pretty sloppy D-to-A converter. All right, so we want to see what goes on with the offset error, the gain error, the differential nonlinearity and the integral nonlinearity. And this is a problem where, whether you use MATLAB or a little bit of programming, or as I do with Excel, this is something where you wouldn't necessarily want to make all these calculations by hand. Just because of, not because it's difficult, but just because there's so many of these calculations. So that's, you want to use something that does the easy but tedious work for you. Okay, so what I've done is I made a spreadsheet in Excel, and I'm hoping you can see this. Well, what I've done is take the bits from A, B, C, D, E, F, G, and those are my 7 bits of my D-to-A converter. Whoops. All right, and so my LSB is 1. I'm then in above these columns, just for my convenience, I'm writing 1, 2, 4, 8, then 15, then 33, then 62. And then I'm going into each of these cells, and for each of the possible values, all the way down, to 127 in this case, I'm going to calculate what is, I know what it should give me, which is the code should translate directly to a decimal or a real number. But what I'm going to get is a slightly different number depending on what I get out of my calculations, adding up each of these bit weights. So for example, let's see, zoom out just a tad. Okay, so I start off with 0, 1, 2, 3, 4, 5, 6. What I see is for the very lowest, then what my DAC output is going to be 0. So that instantly answers the question, if I put in all zeros for my code, what do I get out? I get out a 0. So that answers my question about offset, which says there's no offset for this whole thing. I don't have to worry about an offset error being added in. Now, it would be easy enough to change that, but that wouldn't fit well into this problem statement. Okay, so as far as offset error, that would be 0. And then I really have to go, and I have to go 1 through 127 to get to seeing what happens as I get up into these high numbers. But the way I'm going to calculate it is I'm going to take each of my bits, and I'm going to 10 10 10 10 here, and 0011 0011 on up, 00001111. So I'm reproducing each of the codes, and these are all the possible combination of the digital input bits, recognizing that's going to be 127 different combinations. And then here I'm going to say, take whatever the value in G is, multiplied by its weight, sum that together with F times its weight, E times its weight, D times its weight. And that's exactly what we would do if we were converting from binary to decimal anyway. The only difference is our weights in this case don't turn out to be the weights we expect for a for purely getting that conversion correct. All right, so in this column where I see my DAC outputs, everything looks fine for a while. And I can scroll along, and that's this column, DAC output. So if I scroll that, my mouse would work. Okay, so it goes on. And I made another column here, which is my differential nonlinearity, because all I have to do is look for, did each of these steps step up by 1 volt, 1 count each time? And I can see where, as I'm going up, I get to this point, 15, and then I subtract my 8, my 4, my 2, and my 1 out, and my 15 goes away. I replace it with what should be a 16, but because my fifth bit is 15 rather than 16, I have a DNL error of -1. So I should have gone up by 1, instead I go up by 0, so my DNL is at that point -1. And it continues along until I get down to, let's see, I'm off screen at this point. So I continue on until I get to here. Why is this not scaling along? Okay, there it is. Okay. So at this point, this is where my 33-bit comes back in. Now, if you're paying attention, kind of what happens is I'm counting up, and because of that 16 that really is a 15, or a 15 that should have been a 16, that bit, I'm 1 count below where I should be. When my 33-bit comes in, it corrects and actually overcorrects because it bounces up to 33 when the count should have been 32. So I was at this point below, and then this bounces up. My DNL error is actually 2 because I went from 1 below to 1 above. So that should have been a step of 1, but it's actually a step of, in this case, 3, from 0 to 30 to 33. One of which it should have made, and then 1 being from getting rid of the 15, and the other one from adding in the 33. So actually 3 things are happening right there, only one of which should have made a difference, and what I see is I have a DNL there of 2. And I believe that turns out to be the highest that I ever get. So as we're going along, I'm finding out, if I make this column with basically comparing what's my value here to what was it before, subtract out 1, and I'm looking for any kind of error there. Okay, so I keep going, and eventually I get to the very end, and where I get to 127, and I find out that after all this stuff is added up, my total is only 125. Okay, so 125 for what should have been 127, I put in a code of all ones, which in binary means 127 decimal. Should have got 127 out, instead I got 125. That's going to be the answer for my gain error. Now, if I had had any offset error, I would have had to take that out and take the difference in the code and the difference in the output voltage. But since my code and my first output were both 0, then I can just look at this point. So what I have is a gain error. It should have been 127. And turns out to be only 125. So I've got a gain error of 2 out of 127, so that's on the order of 2%. So that's also, 2 LSBs out of 127 LSBs, so however you want to talk about that. So now I know what my gain error is. In order to do my integral nonlinearity, I took what should have been that line and I'm going to multiply my input code by 125 over 127. So that's basically taking the gain error out. I don't have to worry about taking the offset error out because I've already taken it away. But anyway, so we'll try to zoom in on the calculation, but it's basically count times 125 over 127. This, where's my piece of paper? Okay, so that is basically the line that is the best fit line through the input, through the endpoints, because you think of, okay, if my count equals 0, which is one endpoint, that's an equal sign, then I'm going to get output line that says my line at 0 equals 0, according to that equation. And if my count equals 127, then my line, the line of best fit through the endpoints at 127 equals 125. Okay, so what you see is that's the line I'm looking for that goes through the 0 point and the 125 point. You know, it's just a way of describing, you know, what's that line there. I can also plot that, which I've done. Okay, so I can grab that. If I plot all this stuff, so here, this is a zoom in actually because I wanted to try and find out where the worst case was, and it's going to be someplace in the mid-range, 128, 64-ish. This is actually showing where some stuff is happening, but what I see is I believe this is the line that the pink, I hope you can see that, the pink line is the ideal line, and it's basically going up and it's going directly through, you know, the points at 95, 95, and 70, 70. It's going through all of these points directly, so it's a one-to-one slope. And then here's the actual points are shown as dots. And then the best fit line is actually a little bit low, so it's taking in that the best fit to these points is a slightly lower gain, 125 over 127, and it starts at 0 and it ends at 125. So, you know, this is just a small part of it. If we, I guess I can zoom out of this. No, not there. If I zoom out on this thing and scale it from, auto scale the whole thing on that, and auto scale the whole thing here. Okay, so that's what the overall line looks like. Let me zoom out just a skosh. All right, overall line looks like that. Now it's really hard, you know, why I zoomed in, it's really hard to see what's going on here, but you know, this looks kind of like what a real D-to-A converter, what you might find. You know, it's got 2% error and 3% errors and 1% errors showing up on the weights, which could come from, you know, just a little bit of process variation in whatever the internal components are. Okay, so I know what the line should be that is the best fit through the endpoints. I've already figured out the DNL, but I've had to do that by checking each step by step by step by step, and I can kind of get, I'm using Excel to basically do that by just looking for a change in one step every time I go. Now I can also take the integral nonlinearity by comparing what is the actual value, you know, in this case 0, and then it steps up a 1, 2, 3, all that, to what would it have been if it absolutely followed that slope of not of 1 volt per volt, or 1 volt per step, but if it had followed a line of 125 over 127, which is the slope that best fits the endpoints. Anyway, so I can take that and say, you know, best fit line minus actual and that's my integral nonlinearity. And if you look at a plot of that, it does the same sort of thing we saw in some of the curves that were, true examples of actual D-to-A converters. So it starts at 0 because we go through the endpoints, and it ends up at 127. It's got 0 error because we're comparing to the endpoint, the best line through the endpoints. But in between, the first set of counts is actually, directly where it should be, but it's not on the line that best fits the endpoints. So they're going up by one step exactly each count, but the endpoints are set up so that 125 over 127 is the gain that best fits the whole curve. So it gets a little bit off, and all of a sudden it jumps way down, and it starts to come back to it, and it jumps way up. So if you were to try to describe the integral nonlinearity with a single number for this whole D-to-A converter, it looks like it's between 1.5 and 2 on the positive side, and between minus 1.5 and 2 on the negative. And I actually went through and found found the maximums. Whoops. Found the maximums right for that whole column, and it turns out, it's between plus and minus about 1.7. So that pretty much looks like it's happening on this plot. At the very worst case, which is, it's not at mid-scale, and it's on the order of, I guess, a quarter a scale, which goes along with where the first problems show up, or where the things have both a minus and a plus as far as what's wrong with the individual counts. Okay, so all that being said, then what we're looking for as far as answers for offset error. It's not on the screen. So the offset error in this case is actually around 0. I mean, it is 0 because I didn't build any into the problem statement. The gain error, gain should have been 127 over 127. It's instead 125 over 127. So the gain error is 2 over 127, right? Now some people may say it's 2 out of 128. Depends on if you are counting how many levels, not including 0, or whether you're including 0. But to be honest, with a DAC of any size at all, the difference between 127 in the denominator or 128, whether you're counting as many levels there are or compared to 0, it's going to be about the same. So this is, it's on the order of it's a little less than 2%, but it's on the order of 2%. The INL, no, let's do DNL first. The DNL, the worst was 2 LSBs. We saw that just by comparing, step by step by step by step. And the INL was around 1.7 LSBs. And in this case, I haven't really tried to keep track of if we're dealing with volts or not. Typically, you're not going to have a 127 or 128 volt D-to-A converter, but you would instead have something that's 0 to 10. So all of this could be scaled to a 10 volt reference from 0 to 10 volts too. Or it could be 0 to 5, could be anything. But what we used here, really just keeping track of things in terms of the LSB. Okay, so much for problem 6, and I did see a lot of people were getting the right idea, but they were only plotting it for the individual points that were given, and they didn't look for, what happens when some of these errors start to reinforce each other. So, there were a couple of people that, plotted the points of the 1s, the 2s, the 4s, the 8s, the 16 and 32, and said, well, there's my error. Well, but the problem is, what if, in this case, the 32 and the 64, or I guess what reinforced in this case, because what we had was 1 was 1, so that's no problem. 2 was 2. 4 was 4, no problem. 8 was 8. 16 was 15. Right. This is ideal. This is actual. 32 turned out to be really 33, and 64 turned out to be 62. All right, we got all the combinations, which is where these things can either reinforce or actually cancel each other. As you're going up here, you see that this is a little bit too little and this is a little bit too big, but for everything beyond 30, as you're counting up, this error and this error actually sort of canceled each other out. But then when you got to a point where you included this bit and this bit, this one was 1 lower than it should have been. This was 2 lower than it should have been. So when you had them together, you had something that was 3 LSBs too low. Now that doesn't show up as a DNL because it never happened right at the right, it never changed in one bit, but as far as this stuff adds up to the integral nonlinearity. Across the whole curve, you're going to see this kind of effect. All right, anyway, so I believe that's pretty much wraps up that set of homework, and email me if you have any questions. Have a great Thanksgiving.